welcome to this lecture. We have seen the fields, far fields radiated by dipoles. We have found the radiation resistance of dipole. We have seen that sometimes people prefer to have a monopole because many times the having two poles and feeding it centrally is difficult. Just like you see in police vehicles or in the vehicles when we have a antenna for music or anything. Now, if we want to put the source and then dipoles, then the mechanically it creates a problem, whereas the vehicle body that can serve as a conductor and then monopole will do. And so, if we see the monopole the monopole, I am trying to find, you see the monopoles thing. So, if I have a ground plane and then these, but for analysis we can think that it is like a this by applying image theory we can say that it is just like a dipole without this ground plane. So, the fields radiated also will be same like dipole, only difference is there won't be any field in this lower side because this does not exist actually. So, only in the upper side the fields will be same as the dipole. So, this we can take, and that means you see the field structure will be same as whatever we have described, but what will be the radiation resistance? R radiation is what? R radiation is total power radiated by IRMS square. Now, total power radiated by monopole will be half of the power radiated by dipole, because only the upper hemisphere here is radiating. So, PR will be half of the previous case. So, can I say that our radiation resistance will be instead of 73 ohm, here it will be 36.5 ohm for a monopole, or we can say it as quarter wave monopole. Now, then I think we can see that what happens to the impedance, or what is the loss. So, another thing is what will be the directivity, because we have not seen the directive properties of the two antennas, dipole and monopole. So, but we have all the ammunitions for finding that, because we have found what is the Poynting vector, we have found what is the total radiated power. Now, only job is to put that together. What was directivity? D theta phi. D theta phi, when we introduced the directivity function, we ultimately saw that it is same as 4 pi r square, the Poynting vector average, time average Poynting vector's magnitude divided by PR. So, for dipole we have calculated all this. So, do that. That means, if we put these things, you will get that finally eta naught I m square by 8 pi square r square f square theta a r is the S average portion, or sorry, this I should write as S average, the Poynting vector average. will come this, or this can be further simplified. If we put this 122 pi 4.77 Im square by r square f square theta here. Now, PR we have already found out what is PR. PR is 36.5, just below. In the last test lecture I have derived that. So, now if we put it here, the directivity becomes that 4 pi into 4.77 by 36.5 f square theta. Now, this turns out to be 1.6422. F theta for half wave dipole is now this thing we have seen that maximum value of this is 1. So, maximum directivity D max is nothing but 1.64. So, what is our advantage? What was the corresponding value for current element? It was 1.5. So, directivity is a bit better, 1.6, marginally better. So, direction or directional property wise current element was also quite good, that 1.5 dipole is giving only 1.6. Main advantage is the radiation resistance that we have said, that dipole can really radiate good amount of power. Also, we can find what is the half power beam width. So, for half power beam width, what we demand that F at some let at actually what is half power beam width? If we plot, we have seen if this is z axis, the radiation pattern in the theta plane. So, if this is y, so this is something like this. Now, there for half power beam width, I will have to locate the points where compared to this it will have a half of the power, that means voltage wise, that means f theta will be half of that. So, let at angle theta naught that is happening, that it is having a half of this maximum value. So, we can write f theta naught, f of theta naught, that will have to be 1 by root 2. That means, you put that cos of pi by 2 cos theta naught by sin theta naught, that should be 1 by root 2. So, if you solve for that, theta naught becomes 51 degree. So, if theta naught 51 degree, this side also this angle will be 51 degree. So, this is 51 degree. So, what is the half power beam width? It will turn out to be 78 degree. So, we can say that theta b, the half power beam width of a half wave dipole is 78 degree. Now, how much it improved? For current element it was 90 degree. So, compared to 90 degree, we are getting a 12 degree reduction. That is good, that it is more focused. So, now what is the corresponding things for monopole? For monopole, what is the directivity? If you look at directivity function, what is the thing? Directivity expression you look, the pointing vector is same for monopole and dipole, but power radiated, that is for monopole it is half, that means its directivity will be twice of the dipole. So, directivity for monopole, quarter pole directivity will be 3.28, instead of 1.64 it will be 3.28, because the radiated power is half of the monopole. Okay. Now, we can find out that as a circuit element what is a dipole or monopole. So, what is input impedance Z in. Z in, we know that Z in is R in plus J X in, and what is the input current? So, I in we can say is I m, then sin beta naught L by 2. So, the total time average power delivered to the antenna, if we call that P antenna, that will be I in square by 2 R in. So, it will be I m square by 2 R in sin square beta naught L by 2. If the antenna is lossless, then we can say that this total power delivered to the antenna will be equal to P rad. So, this will be equal to P rad for lossless antenna. For lossy antenna, there is another term, we know that term is because basically for this is a simple antenna. So, R in is actually can be called series of R rad and R loss that we have already seen. Now, that R loss we need to see. Now, actually you see, though we are ideally drawing that antenna is a simple wire, but actually it is, well, I want to make an antenna, it is a rod. So, it has a diameter, it has a, so it is basically a cylindrical rod. So, it has a length, it has a rod, that means through it conduction current will flow and that will put losses. So, that we already have found where we analyze transmission lines, that what is the per unit length resistance of a transmission line made of conductors. So, that we can see. So, let us say that R wire is the per unit length resistance of cylindrical rod or wire, whatever you call it. So, then wire they are saying, okay, but in this case so what is the total power loss? This is the loss resistance, due to loss resistance or due to the ohmic loss, this power loss will be, I have minus L by 2 to L by 2 R where I Z I square R loss. Is this okay? So, time average is a sinusoidal distribution, that is why we are taking half I Z square then. So, from here I can say what is R L, our desired thing R loss, that will be P loss by I whatever input I have given, I in square by 2. So, this is R where it will come out of integration, because it is a, it does not depend on the Z variation. What depends is the current distribution. Now, this I in is different for different length of antennas. So, once you know the current distribution, that means once you know the length of the dipole, then you can find this current distribution. Also you know at the input terminal whether the current is, what is the value of the current. From the current distribution you can always find that. So, if you put that, from that you can evaluate RL. So, this is the way of evaluating RL. This R wire expression is available because transmission line, what is the per unit length resistance, that formula is there in terms of the length, in terms of the diameter and the skin depth and other things. So, conductivity of the antenna. So, this you can put, this is, but the problematic thing is that how do you find this X in? Actually people have found it. So, people have drawn various curves on it, and we can find that out, that there are, for engineers these curves are available, which shows, you see that this is R in versus L by lambda naught, the resistance and A. The interesting thing here is that at the value that L by lambda naught is 0.48, this is actually L by lambda naught is 0.48. At this point the reactive part is 0, and at that point if we find out that the value of this R in, that is 73 ohm. So, this is the resonant point. So, that means not exactly half wave dipole, a bit lower than that, 0.48, because half wave dipole is L by lambda naught is 0.5, but at 0.48 we have some all various diameters, that means whatever may be the thickness of the dipole, that the reactive part goes to 0. So, this is called a resonant dipole, the first resonance. You can see that there are also another resonance that takes place something near 0.75 or 0.8 etc. And but the problem there is, in those places you see the radiation resistance is very high. Why? The reason is, actually if we see that if the length is 0.7 or 0.8, then at the feed point, at the input point, the current is not going to be maximum, the current is going to be minimum. So, that makes the resistance shoots up, and that is why it is a problem there. But if this is a very good one, that near 0.5 we have a resonant point. So, if we make the resonant thing 0.48, then we can have a perfect resonant one, and there the radiation resistance is also quite sizable. But if instead we make it 0.5, we say that there will be some X in is a bit positive, that means it will be having an inductive thing. So, that needs to be balanced. So, by some lumped, putting some lumped capacitor, that can be balanced, or if it is a bit lower, then it becomes capacitive, and that time you can see that there are some inductive things are necessary. In the old police jeeps, you will see that there is a coil at the bottom of the monopole. Actually, that is due to this, that the coil serves the mechanical stability, also it gives tunes out the additional reactance at that point. So, you see this is a good example. So, at 0.5 a thing, actually our X antenna, I can say if we have a perfect lambda half wave dipole, that means L is equal to 0.5 lambda naught half wave dipole, then if you see the actual value, the X is 42.5 ohm, and if we have a monopole, quarter wave monopole, the XA is half of this, 21.25 ohm. Obvious, because in a quarter wave monopole you have only one pole, so your loss is half of the previous one. So, but you can actually, the design of an dipole etcetera all depends on those graphs that I have shown, that whatever additional resistance reactance you are having, you need to cancel that thing, but generally do not take it beyond lambda, because then the problems of very high loss resistance etcetera comes. So, that is why there are there can be problems like this. You see that it is a, I have taken a design problem, that a half wavelength dipole is driven by a source like this, Vs the 100 volt 150 megahertz, Rs is the source resistance is 50 ohm, then it is connected to the antenna and it is having a 1 meter dipole antenna. So, you can very easily find out that at, suppose if we have this problem at, no, let me take a new shade, that at 150 megahertz, this 1 meter dipole 150 megahertz, you can find what will be the lambda. So, 1 meter will be, actually 2 meter will be the lambda naught. So, this whatever is given 1 meter dipole, that will be a lambda half wave dipole. So, we can take that its radiation resistance is 73 ohm and its reactance will be 42.5 ohm, and if we assume that the gauge of the antenna is constructed from a 20 gauge wire, 20 gauge rod. So, that radius turns out to be 4.06 into 10 to the power minus 4 meter, and then we can find out the skin depth. The skin depth will be 5 point, if you do this, you know all the values for skin depth. It is a copper wire. So, you can find skin depth will be this. So, the radius is much larger than skin depth. So, high frequency approximation for wire resistance can be used. What is that? This R wire that we are saying, that at high frequencies we know this is Rs by 2 pi R W. So, and that is 1 by 2 pi R W over omega mu by 2 sigma. So, if you do that, it will turn out to be 1.25 ohm per meter. The ohmic power loss will be found from that P loss is, we have already found this expression R wire by 2 minus L by 2 to plus L by 2 I z square dz. So, the means for a half wave dipole, we can substitute I z value here and integrate it, it is integrable, and from that you will get power loss is R where L by 2 I m square by 2, and from there you will get R L is equal to R where by 2, that is 0.63 ohm. So, total impedance of the antenna will then be that R L plus R rad plus J X antenna, and so this will be, you see that loss resistance is quite small at high frequency compared to 73 ohm resistance, radiation resistance. And so, we can draw this voltage source, then we have a 50 ohm, and then can say that it is getting connected to 73 ohm, then getting connected to 0.63 ohm, and then there is a inductance Js is J 42.5 ohm. So, we can find out what is the current I and. So, I this one I think it will be 100 volt. So, I and will be V s by R s plus Z antenna or whatever antenna, Z antenna. So, that if you do, it will turn out to be 0.765 minus 18.97 degree ampere, and total time average power dissipated in antenna wear loss, that is P loss, that will be half I antenna square R L. So, it will turn out to be 184 milliwatt, and the total time average power radiated P r, that will be half I antenna square R rad. R rad is 73 ohm. If you put it, it will be 21.36 watt, and so radiation efficiency is R rad by R rad plus R L. So, that will be 99.1%. For a microwave antenna, it is typical, even a dipole, such simple structure, but you see it is radiation efficiency is 99%. You can improve this power structure. You can put, because there is a inductance of 40 how much 42.5 ohm. So, to nullify that, we can put a capacitor in series to cancel that, and that value we can obtain that 1 by omega c will be minus x in, that is minus 42.5 ohm. So, from that we can find out that capacitor required in series will be 25 picofarad at that 150 megahertz. With the series capacitor, that means here in this circuit there will have to be a series capacitor. So, of C, the moment we do that, the current will change. So, what will become I antenna we need to do. So, I antenna again if we recalculate, it will be V s by 50 plus 73.63. So, it will be 0.809, and so you see here I antenna is having no phase angle, it is because of the introduction of C, it is now in phase with the voltage, and P radiated power, that will also improve 23.9 watt compared to 21.36 watt earlier. So, this is the impedance proper if we balance out the near field, that storage. So, this capacitor will now change that, and the antenna will be able to radiate more power due to this. So, with this I conclude this monopole and dipole things, but one thing is remaining, that also apart from all these antenna with this type of dipole antennas, they need another device which is called Belan. For their structure they need it, that I will introduce in the next class. Thank you.